Hello everyone, welcome to the 20th edition of the IChemE Safety Centre Safety Lower. My name is Craig Wright and I'm a Process Safety Specialist with the Safety Centre. During this webinar we will be focusing on the cost of corrosion. We see it occurring in all aspects of our life, from the modes of transport we use, to the equipment in our gyms, through to plant, equipment, pipelines and structures. Within the webinar, we will discuss two incidents that have occurred in similar industries and provide you with an opportunity to ask questions at the end. We have a questions box in the webinar, so please put all questions in there as we're going along. The ISC purpose, so we assist organisations from industry, government and universities focusing on high hazard activities to improve their process safety performance by sharing best practices and resources through podcasts, ISC publications, webinars and safety law documents. We also provide a unique opportunity to enhance process safety performance through training via our internationally renowned facilitated case studies and process safety leadership and culture programme. Here is pictures of the IChemE industry and operating partners, and we also support universities. So what is corrosion? Corrosion is one of the largest causes of plant and equipment breakdown in the process industries and is a dangerous and extremely costly problem which can result in loss of primary containment and even electrical fires due to corroded electrical contacts. Corrosion is an electrochemical reaction that appears in several forms such as chemical corrosion and atmospheric corrosion. When acidic substances come in contact with metals such as iron or steel, rust begins to form. Rust is the result of corroding steel after the iron particles have been exposed to oxygen and moisture, and if not managed effectively, can have catastrophic consequences. Case 1. On August 6, 2012, a refinery experienced a catastrophic pipe rupture on a 52-inch long component of the 4 side-cut 8-inch line. At the time of the incident, light gas oil was flowing through the line at a rate of approximately 10,800 barrels per day. The ruptured pipe released flammable high-temperature light gas oil, which then vaporised into a vapour cloud that engulfed 19 employees. The incident resulted in around 15,000 people from the surrounding communities seeking medical treatment. The rupture was the result of sulfidation corrosion, which causes thinning in iron-containing materials due to a reaction between sulfur compounds and iron at temperatures ranging from 450 to 1000 degrees Fahrenheit. The pipeline that ruptured was constructed of carbon steel, which corrodes at a much faster rate from sulfidation than other typical alternative materials due to variances in silicon content. So some key findings in this case was that the organisation did not follow the subject matter experts' recommendations to help prevent pipeline failures due to sulfidation corrosion. 10 years prior to this event, SMEs of corrosion recommended an internal inspection should take place, or that the pipeline that ruptured be upgraded to a more suitable material. The senior management rejected the SME's proposal for turnaround work due to a historical integrity document that stated the pipeline should retain integrity until circa 2016. This resulted in the organisation believing there was a lack of data to justify the work or support the profit improvement project, even though they had a sulfidation failure prevention initiative in place. An upgraded inspection programme was then implemented for materials subjected to sulfidation corrosion. Emergency response refresher training was required for personnel due to a lack of understanding of procedures post-incident. Case 2 is a chlorine release. On July 20th, 2003, a release of chlorine gas occurred from a chemical plant which resulted in 7 plant workers being injured and a shelter-in-place advisory warning being issued for residents within a half-mile radius of the plant. During the investigation, the heat exchanger was cut open for inspection, which showed 3 holes in the tubes and a build-up of corrosion products at the bottom. It is believed that a historic arc welding process in the year 2000 was a major contributor to the heat exchanger failing. After a matter of years, the natural corrosivity of the brine thinned and welded metal, resulting in small amounts of chlorine being able to contaminate the brine. A chlorine-induced chemical attack then occurred, enlarging the holes and allowing more chlorine into the brine. The increase in chlorine with the brine led to the coolant pump seals failing, which released chlorine to the atmosphere, which was then able to enter the control room through the air ventilation route. The release to atmosphere was prolonged due to the requirements for manual valves to be closed to isolate the system. Key findings. The organisation had a culture of risk normalisation due to multiple plant leaks. Also, a similar incident occurred 2 years earlier at the same facility, and the learnings from this incident were not implemented. There was a lack of consideration into automated shutdown systems on the plant, including isolation valves, as it was still relying on manual operations. The heating, ventilation and air conditioning design was inadequate to protect safe areas such as the control room from hazardous substances. Management of change failures, inadequate risk assessments, and poor emergency response on site and for the public were all key findings. So lessons for management from both incidents were: ensure that there are written procedures on the requirements to be in place to ensure continued corrosion monitoring occurs. Ensure that an emergency response team and equipment are available within the organisation for multiple scenarios. Ensure that changes to scope are adequately assessed and approved prior to any work taking place. Conduct a full review of any SME advice that you receive. Ensure there is maintenance management systems that defines how work is identified and scoped. Have in place an effective management of change process to adequately record changes from normal operations, such as the welding operations highlighted, as this is a deviation from normal operations. Ensure risk assessments are reviewed and updated at adequate time intervals to reflect current conditions. Liaise with local residents on the risks associated with plant or the process and steps to take in an emergency. Lessons for engineers and supervisors. Make sure to follow company rules and operating procedures to protect workers. Complete simulated emergency response exercises. Ensure site personnel concerns for stop activity are addressed and suitable feedback provided. Ensure that all scope changes are adequately risk assessed and documented. Any changes must be reviewed to ensure conditions are suitable for ongoing operations. Ensure plant is designed to allow automated isolation in an emergency situation, including safe areas such as control rooms. When issuing a permit to work, ensure that all hazards specific to the task are identified and that controls are implemented to manage these hazards, such as nearby weeps and seeps, passing valves, etc. Perform adequate HAZOP hazard LOPA studies into enhancing plant and equipment within a suitable review period. Have daily or shift briefs to ensure site teams are aware of issues associated with the plant and process. Lessons for operators. Complete start and end of shift plant checks for abnormal conditions. Report all abnormal conditions and, if safe to do so, take the appropriate action. Ensure worksite visits are effective pre-job risk assessment discussions take place. Perform regular plant checks on all work to ensure it is being performed as required and following the permit to work controls. Audit if required. Stop the job and report any deviation from the permit to work system, including change in surroundings. Ensure sufficient handovers are in use, documenting all activities. That takes us to the close of the two corrosive examples of where it can go wrong in industry. I would like to just take this time to share an example that's certainly occurred to me in an offshore asset, where very similar to case study 2, we had contaminated our cooling medium system through a corroded heat exchanger, but we had hydrocarbons enter the system. The system itself, the cooling medium pumps, they were located in a safe area. So we'd ultimately created a hazardous area within a non-hazardous area on our asset, and the fluid itself was being pumped around the entire facility. Originally non-hazardous, but we had now made it a full hazardous systems. We had to continually depressurize and repressurize the system with nitrogen to vent it off to a safe area that we then made a non-safe area because there was hydrocarbons coming out there, to try and displace the system and make it clean again. When I was reading case 2, I recalled the risk assessments that there was no mention of pump seal failures. So it kind of brought it home a little to myself that potentially we were just lucky that we did not cause any issues of pump seal failures. So case study 2 could have simply quite easily happened to us in an offshore installation. We've also another example of where we used to re-inject oil back into a reservoir offshore should we have to shut the process down. And on one of the recycle lines, there was a 2-inch sample elbow that over time, because normal operations were not to have this system online, the inspection program wasn't always carried out on the line. And one day the 2-inch line failed on the elbow. It had corroded right through, and we were pumping it anywhere in the region of around 20 bar to kill the well to get into the reservoir. So we'd a 2-inch rupture due to corrosion where oil was spraying on the offshore asset, and we ultimately had a process safety incident and an environmental incident all in the one, due to the location being over open grating. So that 2 samples I can think on relate to these 2, where I first-hand experienced the cost of corrosion, and it not only can it impact your reputation, it's impacting the bottom line for the business also. So step 1, make sure it's safe. We adequately assess it all. If there's any questions, please take some time to put them in the box at the side. Got one question here about the first example on permits. So yeah, the first example that I gave was how we turned a non-hazardous area into a hazardous area. So what we had to do was all permit to work controls. We'd changed everything on the asset from cold work permits to hot work permits. So everything had to be gas tested. So it required quite a big change for a couple of weeks, where we were normalised to, if you were in modules 1, 2, 3, that it was non-hazardous, but all of a sudden you had to try and increase your awareness that you were now working on hazardous systems. So auditing was one aspect that significantly increased on the asset to try and keep it safer, where those working in the non-hazardous modules were subjected to extensive auditing just to keep on top of the significant change from non-hazardous to hazardous area. Okay, if that's all, I'd like to thank you all for taking the time to dial in this morning to the webinar. Thanks very much and stay safe.